Welcome to the deep dive. Today we are taking a really necessary and fundamental plunge into the very bedrock of material science, thermodynamics. Our mission is to take Chapter 1 from a core text on the subject, the introduction and definition of terms, and translate that dense vocabulary into immediate usable knowledge.
It was essential groundwork. I mean, when you hear the word thermodynamics, you might think of its origins, the Greek words for heat and power.
Right, steam engines and all that.
Exactly. That's where it started, studying the conversion of thermal energy into mechanical work. But what's fascinating is how the scope just widened. It's now the universal framework for understanding all equilibrium states. It's really the language of stability.
So we're moving way past just engines. We're talking about how materials exist and change. And to do that, we have to start by drawing a line in the sand. We have to define the system.
That's it. The system is the specific, small part of the universe we're choosing to study. And then everything else, that's the surroundings.
Everything that can possibly interact with it.
Absolutely. And those interactions are entirely controlled by the walls or the boundaries we decide to put up. Defining those boundaries is, the first critical step in any thermodynamic problem.
Okay, let's talk about those boundaries then. How do we classify them based on what they let through?
We classify them based on two things: energy and matter. For energy, a boundary can be diathermal.
Diathermal.
Yeah, it means it allows thermal energy heat to pass through. Just think of a metal pan on a stove.
And the opposite of that would be?
The opposite is adiabatic. An adiabatic boundary prevents any heat transfer. It's like a perfect thermos, completely insulating the system.
Okay, so that's energy. What about for matter?
For matter, the walls are either permeable, which lets matter pass through freely, or impermeable, which blocks everything. It holds the composition constant.
Is there anything in between?
There is. There's the semi-permeable boundary, which is fascinating. It only allows certain components to pass through, like a very specific filter.
So based on those walls, we get our three classic system types. First is the isolated system.
Right. Walls are both adiabatic and impermeable. No energy, no matter, no work. Everything inside is just locked in, constant.
And you have the closed system.
A closed system is impermeable to matter, so the composition is fixed. But it's diathermal, so energy can cross the boundary. You can do work on it, or it can do work, but no mass gets in or out.
And finally, the most common in the real world, the open system.
That's the one, exchanging both energy and matter. It's the most complex, sure, but it describes almost everything, like a chemical reaction happening in a beaker.
Okay, so once we define the system, we need to understand what happens when we just leave it alone.
And that brings us to equilibrium. It's a state of macroscopic rest. The system stops changing spontaneously because all its internal driving forces are balanced out. Thermodynamics is fundamentally the study of matter and energy at equilibrium.
This is where the big intellectual jump happens, right? I mean, if you look at a gas, you have something like 10 to the 24th molecules bouncing around.
Impossible to track.
Exactly. Tracking that microscopic state is completely impossible. So thermodynamics simplifies everything. We just shift our focus to the macroscopic state.
And this is the genius of it. It turns out for a simple system-fixed composition, just interacting through pressure and temperature, you don't need a billion parameters. You only need to define a tiny number of variables to lock down the entire state of the system.
And according to the Duhem postulate, that number is often just 2, usually temperature T and pressure P.
Yeah.
How can just 2 variables be enough to define an entire system?
Because once you fix 2 of them, all the other properties, like volume or internal energy, they become dependent variables. They're mathematically locked in. That simplification is the foundation of all of this.
Let's unpack that. If a property like volume only depends on the current state, we call it a function of state, meaning it doesn't matter how it got there. The history is irrelevant.
Exactly right. Think of volume V. Imagine plotting the relationship between volume, pressure, and temperature on a 3D graph. It forms a surface. Any equilibrium state is just a point on that surface. If you go from state 1 to state 2, the total change in volume, delta V, is exactly the same no matter what path you take.
A wiggly path, a straight path, it all ends up with the same change in volume.
The path doesn't matter. And because the path doesn't matter, it means the differential change, dV, has to be what we call an exact differential.
And that's what lets us use calculus here.
Precisely. That exact differential lets us express any tiny change in volume by measuring 2 sensitivities. First, how sensitive volume is to pressure changes at a constant temperature.
Okay.
And second, how sensitive volume is to temperature changes at a constant pressure. And those sensitivities, we can measure those in a lab.
And those are the material properties we use in engineering every day.
They are the change in volume with pressure
Mm.
that defines the isothermal compressibility, beta T. It's the fractional decrease in volume as you squeeze it. It tells you how resilient a material is.
And the other one, the change with temperature.
That defines the coefficient of thermal expansion, alpha P, the fractional increase in volume as you heat it up. If you know those two properties for a material, you can predict any small volume change. It's an incredibly elegant way to connect calculus to real material behavior.
Let's switch gears a bit to the ideal gas law. It's this perfect expression of simplicity built from history and observation.
It really is. You have Boyle, way back in 1660, finding that pressure is inversely proportional to volume. Then, a century later, Charles finds that volume is proportional to temperature.
And the theoretical ideal gas is basically just a model invented to obey those rules perfectly.
Yes, but the huge leap forward came from Gay-Lussac and Regnault. They measured the coefficient of thermal expansion, alpha P, for these gases, and they found it was almost always the same number, 1 over 2, 73.15.
And that single fraction, 73.15, defined absolute zero.
It did. If a gas shrinks by that fraction of its volume at 0 Celsius for every degree you cool it, well, then it has to hit zero volume at minus 273.15 Celsius. That gives us the absolute temperature scale.
And once you combine all that with Avogadro's work on moles, you get the big one, the ideal gas law for 1 mole.
PV equals RT.
Now here's where it gets really interesting for me.
Yeah.
P times V. The units are actually energy. Pressure is force per area, volume is distance cubed. So P times V is force times distance. That's work. It's energy.
Exactly. The gas constant, R, isn't just a random number. It's the universal conversion factor between the pressure-volume world and the temperature world. Its value in SI units, 8.3144 joules per degree mole, tells you exactly how much energy is in that system.
Okay, before we get to the famous 3 laws, we have to talk about the one that came first but was named last.
Yeah.
The Zeroth Law of Thermodynamics.
Right, it seems almost too obvious, but it's fundamental. It's what establishes temperature as a real measurable state variable.
It's the if A equals B and B equals C, then A equals C law, but for heat.
Pretty much. If system A is in thermal equilibrium with B and B is with C, then A must be in thermal equilibrium with C. It defines what thermal equilibrium even is, a state with 0 temperature gradient. Without it, we couldn't trust our thermometers.
Now that we have these variables, P, V, T, we need to classify them based on scale.
Right, we have 2 types. Extensive variables, which depend on the size of the system. Think total volume, V prime, or total mass. If you double the system, you double those variables.
Then the other type.
Intensive variables. They are independent of the system size. Pressure, temperature, density. And here's the key. If you take an extensive variable and divide it by the amount of stuff like molar volume, V, which is total volume divided by moles, it becomes intensive.
Which brings us to visualizing all this with phase diagrams. For a simple unary system, like water, we plot pressure versus temperature. The big areas on that map are the homogeneous regions.
Right, single phases, all liquid or all vapor or all solid.
But the curves are where the action is. Those are the heterogeneous regions where 2 phases, say solid and liquid, are coexisting in equilibrium.
And where all 3 curves meet.
The triple point.
The unique triple point, where all 3 phases coexist in perfect balance. Now, if we move to a binary system like an alloy of aluminum oxide and chromium oxide, we usually hold pressure constant and plot temperature versus composition.
And this is what engineers use to design alloys. When you have a composition that falls into one of those 2-phase regions where you've got both solid and liquid, how do you know how much of each you have?
That's where the lever rule comes in. It is an incredibly powerful tool. If your overall alloy composition, let's call it C, sits between a liquid boundary, L, and a solid boundary, S, at some temperature, the relative amounts are determined by the inverse lever arm principle. The fraction of solid you have is proportional to the distance from your composition C to the liquid boundary.
Wait, say that again? The amount of solid is proportional to the length of the liquid line segment.
Exactly. It's a bit counterintuitive, but it works like a balance beam. You're balancing the total composition C between the 2 phases that exist. The lever rule is how you predict what fraction of your molten steel has solidified at a given temperature, which directly controls its final strength.
So we've defined the players and the rules. Now, let's just quickly run through the 4 guiding principles. We did the Zeroth Law, which gave us temperature.
Next is the first law. This is conservation of energy. Energy can be converted, heat to work, but the total energy of the universe is constant. And it introduces internal energy, U prime, as a new extensive state function.
Why do we need another state function?
Because P, V, and T only describe the external state. We needed U prime to account for the energy inside the system itself, which changes when you add heat or do work.
Then the big one, the second law. This one tells us which way time flows.
It does. It dictates the direction of all spontaneous processes. And it introduces our third fundamental state function, entropy, S prime. The key takeaway is simple. The entropy of the universe never decreases. It can only increase or stay the same.
And finally, the third law. This one deals with the ultimate limit of cold.
The third law gives us our baseline. It states that as temperature approaches absolute zero, the entropy of a system also approaches zero, assuming it's in perfect internal equilibrium. This also gives us the unattainability principle. You can never actually reach absolute zero. You can only get closer and closer.
That was an essential overview. We started with system boundaries, established that the macroscopic state only needs two variables, explored the beauty of state functions, and saw how PVRT defined absolute zero. Then we hit the four laws governing T, U prime, and S prime.
And if you connect it all back, you see the elegance. We talked about those complex partial derivatives, isothermal compressibility, and thermal expansion. For a perfect ideal gas, the math collapses. Beta T becomes simply 1 over P. Alpha P becomes simply 1 over T. That simplicity really shows the power of these foundational concepts.
That symmetry is key. So you now know that volume, V, is a state function. It's independent of the path. But here's something to think about. Work and heat are not state functions. They depend entirely on the path you take. So how would the amount of work compare if you go from state 1 to state 2 by changing the pressure first versus changing the temperature first? Since the change in internal energy is fixed, any difference in work has to be balanced by a difference in heat. Something to mull over until our next deep dive.
Thank you for joining us for this essential deep dive into the foundations of materials thermodynamics.